Hi, welcome once again in this course of indefinite integrals, and today we are going to do lesson number 17 in the series, that is transformation and substitution, both part 2. So in the previous lesson we have understood that that in some of the integrands we have to apply both of the techniques, that is transformation and substitution. So let us see some more integrands of that kind. So this is the integrand form. We can see that 1 over a sin x plus minus b cos x, 1 over a plus minus b sin x, 1 over a plus minus b cos x, or 1 over a sin x plus b cos x plus c. So you can see that in denominator we will have sin x or cosine x or both, and the combination is very easily to understand what the combination will look like. So for this, what transformation we have to do? First of all, we have to do the trigonometric transformation, and then you have to substitute. So the trigonometric transformation is like that. You know, the identity of sin x can be written in form of tan as 2 tan x by 2, 1 plus tan square x by 2. And again for cos x you can write 1 minus tan square x by 2 divided by 1 plus tan square x by 2. So these two values of sin x and cos x in form of tan can be replaced in this integrand, and then you have to transform, and after that we have to substitute tan x by 2 as t. So let us try to understand with the example. So suppose I have the integrand as 1 by 3 sin x plus 4 cos x. So of course sin x can be replaced with 2 tan x by 2 by 1 plus tan square by 2, and cos x should be replaced with 1 minus tan square x by 2 divided by 1 plus tan square x by 2. So after simple manipulation you can get that 1 plus tan square x by 2 and 1 plus tan square by 2 are the same. That means they are the common denominator in the denominator of the whole fraction. So you can take this at the top, and 1 plus tan square x by 2 should be sec square x by 2, so this can be written at the top. And in the denominator you will get 3 times 2 6 tan x by 2, and this can be further manipulated to write this 4 minus 4 tan square x by 2. So you can see that this 6 tan x by 2 plus 4 minus 4 tan square by 2 is a quadratic of tan, and of course this tan x by 2 can be substituted because the derivative of tan x by 2 is actually available, at least the factor of it. So t is equal to tan x by 2 will be substituted, so the dt will be half sec square x by 2. So this sec square x by 2 dx is present in the top, so this can be eliminated or replaced with 2 dt, and of course wherever you see the tan x by 2 you have to place t. So you will get this integrand now in terms of t, that was 6t plus 4 minus 4t square in the denominator, and in the numerator there is only 1. So it is actually in the form of 1 by ax square plus bx plus c, and this can be done by the process of completing square, as you know. So for this you want to make the leading coefficient, that means the coefficient of t square is 1, and for that you can take this negative 4 common, and so this will be t square minus 3 by 2 t minus 1, and after further simplification you can get t minus 3 by 4 the whole square, and this minus 9 by 4 minus 9, and this can be done further, and so you will get finally this quadratic as the difference of two perfect square as 4 times 13 by 4 minus t minus 3 by 4 the whole square, and of course the 13 by 4 can be written as root 13 by 2 the whole square, and after placing this into the integrand you will get this integrand, and after applying one of the special line you will get this answer. But of course this answer is actually in terms of t, but you need to find the answer in terms of x. So you know that t was actually tan x by 2, so you can simply mention in the final answer that t is tan x by 2. That is enough for your correct answer. So now this was actually one of the form in which we have I have done the complete answer. Let's do another kind of example in it, where transformation and substitution both will be applied. So this is another kind of integrand, and this is a very unique type, and you have to remember this type. This is x square minus 1 over x to the power 4 plus 1. So in this this kind of integrand, you have to divide the numerator and denominator with x square, and there is no actually algorithm or simply any set of rules, so you can simply identify that we have to divide with x square or not. But after a lot of practice, you can develop this technique. But I simply suggest you to remember or practice more on such kind of problems, so that you can get familiar with the technique in which we have to divide with x square. So this is one of the form, that x square minus 1 over x to the power 4 plus 1, and for this we have to divide with x square. So you will get 1 minus 1 by x square, and in denominator you will get x square plus 1 by x square. And you can see that the numerator is 1 minus 1 by x square. Now you can see that the derivative of, means what is the function whose derivative is 1 minus 1 by x square. So your answer is the derivative of x is 1, and the derivative of 1 by x is 1 minus negative 1 by x square. It means if we can if we will be able to construct this x plus 1 by x format in the denominator, we can simply substitute this x plus 1 by x as t, and that is the main purpose of this method. So actually you see that x square plus 1 by x square, actually x square plus 1 by x square is present in the denominator, and this can be easily made in the form of x plus 1 by x. And why so? Because see what happens. This is x square, this is x square, and this 1 by x square can be written as it is, but you can see that this x and 1 by x can be treated as a square and b square, I mean a and b, and this is what a and b. So I have multiplied with 2 so that it can be the formula of a plus b the whole square. And now this extra 2 is added there, so I have to compensate that with by subtracting it. So this will be now in the denominator x plus 1 by x the whole square and minus 2. So we have this x plus 1 by x in the denominator, and we can substitute x plus 1 by x as t, and we can easily see the derivative of that is present already in the top. So substituting t is equal to x plus 1 by x, we will get dt as 1 minus 1 by x square dx, and of course we will have this kind of integral in the form of t, sorry, integrand in form of t, and so that is the final integral where t was x plus 1 by x. Another example is, here you can see that the top there was x square minus 1. In the same category we may have at the top there is x square plus 1, but notice in the denominator we will always have x to the power 4 plus 1. There is no minus sign in the denominator, and the reason is very easy to understand, that whenever you divide with x square in this technique, this must give you x to the power x square plus 1 by x square, and we are actually making the perfect square of x plus 1 by x or x minus 1 by x. So of course a square and b square has both positive signs, therefore there should be no negative sign in the denominator. So now you can see that there is a plus sign, and of course the derivative of x minus 1 by x should be made here. I mean the derivative of x minus 1 by x can be foreseen here, and so we have to transform this x square plus 1 by x square in the form of x minus 1 by x. So here what I should write, that is 1 plus 1 by x square dx as it is, and this will be x square minus 2 times a into b, and this is b square. So of course in the denominator we will get x minus 1 by x the whole square and plus root 2 square, and substituting this x minus 1 by x as t, we will have the integrand in form of t, and then we can proceed. So you can do this. So I have not done this question completely. Now in some questions this x square plus 1 and this x square minus 1 will not be seen in the numerator, but still we can see the x to the power 4 plus 1 in the denominator. So how can we deal with such kind of question? Let us see. So in this integrand we can see that the numerator is only having a constant. So we can simply take this constant out and we have to multiply and divide with 2. So what I have done, you can see this is, suppose I multiply and divide with 2 here, you will get this thing. And this 5 can be taken out and 2 is of course there. But in numerator you will have a 2. So what we can do now, we have to add 1x square and subtract 1x square. So you can see that x square plus 1 minus x square minus 1 can be evaluated to get 2 again back. So I have added 1x square and subtracted 1x square so that I can see x square plus 1 and x square minus 1 both in the top. Now we will split it into two parts, the two integrands, or we can see that the first integrand will form x square plus 1 divided by x to the power 4 plus 1, and this x square minus 1 divided by x to the power 4 plus 1. So you can see that both of these integrands are handled in the previous examples, and they are sometimes called algebraic twins when they appear simultaneously in a particular kind of question. Alright, let us try to apply this method to deal with this kind of problem. Here you can see there is a trigonometric function, but the transformation can be done to convert this trigonometric function into the form of one of the trigonometric twins, or the method we have developed in the previous example, and then we can do the question. So suppose I have square root of tan x dx. So for that the substitution should be t square, and we are not substituting t because we want to remove this square root. So t square should be substituted for tan x, and so the derivative will be 2t dt in the left hand side, in the right hand side will be sec square dx. And we have to also substitute dx, so we are now going to find the value of dx from here. So dx can be written as 2t by sec square x, and we are lucky to find that sec square x is also written as the form of tan, and that is 1 plus tan square x. And since tan x was t square, so we can substitute that t here, or t square here, and we will get dx as this 2t over 1 plus t to the power 4. So let us substitute these two things in the original integrand, and so it is root tan x can be replaced with t, and this dx can be replaced with 2t by 1 plus 2 t to the power 4, and from there we get this integrand 2t square by 1 plus t to the power 4. And again you can see that 2t square can be written as t square plus 1 and plus t square minus 1. I have just added, actually first I have written this 2t square as t square plus t square, and then added 1 and subtracted 1. So that now I can split it into two parts, that is t square plus 1 over 1 plus t to the power 4, and t square minus 1 by 1 plus t to the power 4, and you better know how to handle with it, because this is now algebraic twins and you know how to do this. Let us apply the same thing in this particular question, and this is a very popular one. You can also find this question in some books. So this is what the integration of root tan x minus root cot x. So of course this root cot x can be written as 1 over root tan x. So this t square was written as tan x, you know, because we don't want this square root, and dx was actually evaluated in the previous example, so that will be the same in this one. So this will be 2t by 1 plus 2 to the power 4 dt. So let us try to replace this. So root tan x should be t now, and 1 over root tan x should be 1 by t, and of course dx will be 2t over 1 plus 2 to the power 4 dt. So after simplifying this, they will get t square minus 1, and by t, so this t and this t will get cancelled, and we will have 2t square minus 1 by 1 plus t to the power 4. And now this 2 can be removed because it's a constant, and you can see it is clearly one of the algebraic twins, t square minus 1 by 1 plus t to the power 4. So we can handle this question easily. So in this particular lesson, I am also I have only given the I have not given the complete answer for few questions, but I understand that you understand the method after better. So this lesson number 16 and lesson number 17 was based on the technique of transformation and substitution both. So you may find a variety of such integrand form in which we have to apply both of them, but I have picked only few integrand form which is actually in your syllabus and also very important to understand. So I hope you understood this technique also. Thanks for watching this lesson. Thank you very much.